Last time we looked at the de Groot model. This was a discrete time deterministic model, but with a continuous state space. The opinions took values in the real numbers or in some bounded subset of them. Today we are going to look at a model which is stochastic and continuous time, but the space of opinions is discrete. In fact, it's going to be finite, and we are even going to look at the setting of just two opinions. So I'll share screen. Okay, so we are going to introduce today a stochastic model known as the water model. We'll build it in continuous time. And to start with, we will look at it on the complete graph for simplicity. And then we'll go on to look at it on arbitrary graphs. We have the complete graph on n nodes, which is denoted k sub n. And we'll assume it's directed. So each edge should be thought of as two edges in opposite directions. Every vertex has an opinion, and that opinion is either 0 or 1. It's not difficult to extend the model to any finite set of opinions. The analysis is much the same. Just to simplify notation, and not get distracted by unnecessary details, we'll look at the case of two opinions. The process is going to be defined in a way that's quite similar to the rumor spreading model we considered earlier. So there are going to be independent Poisson processes, one associated with every vertex, and they are all of the same rate. We scale time so that the rate is taken to be 1. So each vertex has a clock sitting on it, and the clock rings after independent exponential 1 times. Okay. And every time the clock rings, the vertex V chooses a vertex W uniformly at random, might be itself, an independent of the past, and then it copies the opinion of the vertex W. Okay, so the name of the model, it's not a realistic model of voters, but if you think of it as a highly stylized model of voters in a political system, so there's a two-party system, there are only two choices, and each voter has a preference for one or the other of the parties. The nodes of the graph are associated with the voters. And then a voter V decides to talk to somebody and chooses who to talk to uniformly at random. And they simply adopt the opinion of the last person they talk to. So they are not hard to persuade. If I talk to you, then I become convinced of your opinion and I adopt it. Of course, talking is bidirectional, but here the direction is by who initiated the conversation. So if I initiate the conversation, then I'm asking you for your opinion, and then I simply adopt your opinion. And this is the pull model. So when I talk, I ask somebody's opinion and adopt it. You could equally well have defined this in terms of a push model, which is what we did for rumor spreading, but the two are perfectly symmetric. Okay, so this is the model. Take a moment to make sure that this is completely clear. I've given you all the information you need to simulate the system starting from an arbitrary initial condition. So convince yourself if you're able to do that. Could you write a computer program to simulate this model? Okay, so what are the questions we are going to be interested in? We want to know if eventually all vertices reach consensus on one of the two possible values, 0 or 1. So do all voters end up supporting political party 0 or political party 1? And if so, how long does it take? And what's the probability of which party everybody chooses to vote for? Okay, so these are natural questions for this model. And we are going to begin by describing this model as a Markov process, or a continuous time Markov chain. So we'll denote by xv of t the opinion of vertex v at time t. And in this model, the opinion can take only one of two values, 0 or 1. And boldface x of t is going to be this vector of opinions, one at every vertex. Hopefully it's clear from the verbal description of the model that the boldface process is a Markov process because it's built on top of Poisson processes, which are memoryless. If I tell you what the opinions of all the vertices are at time t, then which of them is going to initiate the next next conversation or next phone call, who is going to talk to whom, who's going to talk is independent of the past because of the memoryless property of the exponential distributions. It doesn't matter that this vertex has not talked for a long time and that this one only recently talked to somebody. They both wait an exponential amount of time before next talking to somebody. And by the memoryless property of the exponential, how long they have been waiting since they last talked doesn't matter. Okay, so there's independence of the past in that way. And then once you pick who's going to talk, who they choose to talk to is chosen uniformly at random, independent of the past. So again, it doesn't depend on the past. And once you pick who's talking a vertex v, who they are talking to a vertex w, the change of opinion that happens only depends on the opinions of vertex v and w at this time. It doesn't matter how recently they changed their mind or how long they've held that opinion. In practice, of course, you might think that these things should matter. Somebody who's held the same opinion for 10 years is much less likely to change their opinion than somebody who's held it for 1 week. But this model doesn't capture all those things. Okay, so the simplified model is a Markov process. And the state space is a vector of zeros and ones, and the vector is indexed by the vertex set. Every element corresponds to a vertex. Okay, and what's the size of the state space? If there are n vertices, the size is 2 to the n. It's the set of all possible subsets of the vertex set. So its size is 2 to the n, and this is large. Okay, so in principle, one could answer the questions about which opinion is adopted, or what's the probability that everybody reaches consensus on one. We can answer that just by solving a system of simultaneous linear equations, but the number of equations is equal to the size of the state space, and that's huge, so this is not practical. And likewise for the time to reach one of the consensus states. Again, in principle, it could be solved, but in practice, not on state spaces of this sort of size. Okay, so numerical linear algebra is not the best way to answer these questions. Okay, in fact, for this model, they would work because there is a simpler model on a much smaller state space, and we'll discuss that next. Okay, and this model is You might have guessed this by analogy with the rumor spreading setting. There, the symmetry in the model told us that we only need to keep track of how many nodes have learned the rumor and not which of them have learned the rumor, because it's the same for every subset. And a similar thing is true here. We only need to keep track of the number of nodes with each opinion 1 or 0. And the total number of nodes is n. So if I tell you how many have opinion 1, you know how many have opinion 0. So it's enough to keep track of yt, the number of nodes with opinion 1 at time t. Because it doesn't matter how much time each of these nodes spent in that opinion, or how long has elapsed for each of them before they last talked to somebody. All that is irrelevant. And all that matters is there are this many nodes with opinion 1, and they are going to talk to somebody after exponential times, and similarly for those with opinion 0. Okay, what's the state space of this process? Clearly, the number of nodes with any opinion has to lie between 0 and n. So that's the state space. Let's write down the transition rates for this continuous time Markov chain. And I claim it's the following: the rate of going from k to k plus 1. Okay, suppose there are k nodes with opinion 1. How do we write down these rates from the verbal description of the process? We want to ask what happens in some small time delta. So every time somebody talks to somebody else, k can change. The number of nodes with a certain opinion can change. Now, if the time interval is chosen very small, then at most one phone call happens in that time. Maybe none, maybe one, but the chance of 2 or more is negligible. If you like, you can think of this in terms of, okay, so why is that true? So what's the aggregate process of phone calls? Every vertex makes phone calls at the increment times of a unit rate Poisson process. That's how we describe the model. That's for a single vertex. Now, if you look at all possible phone calls, this is the superposition of the Poisson processes corresponding to each of the vertices. And these are independent Poisson processes. We were also told that in describing the model. And you know that the superposition of independent Poisson processes is a Poisson process. So the total stochastic process of all conversations or phone calls is a Poisson process of intensity n. And so the time, and we know for a Poisson process that you can have only one increment at a time. It can't jump by 2 or more steps at a time. So if you look at a small time interval delta, there's either 0 phone calls or 1 phone call in that time interval. And the probability of 2 or more is little o of delta. Okay, so what needs to happen for a transition from k to k plus 1? So what needs to happen is that we need in this time interval delta for one more node to have opinion 1. That means a node which originally had opinion 0 before the start of this time interval has to change its opinion to 1. And how can that happen? It can only happen if that particular node V, a node V with opinion 0, firstly decides to make a phone call, then it chooses W uniformly at random, and the W it chose had opinion 1. So a node with opinion 0 has to contact a node with opinion 1, and that's what results in this change. So maybe let me stop sharing this for a moment and try using a picture. Okay, so we have here a bunch of nodes with opinion 0. And there are k of them. And then we have a bunch of nodes here with opinion 1. And there are n minus k of these. Okay, and then, so I described the process of communications in a node-centric way. But just as for the rumor spreading model, you can change the description to an edge-centric model. And that means the rate at which any vertex contacts any other vertex is 1 over n. So this vertex here wakes up at rate 1. So at the jump times of a Poisson process of rate 1, it decides to make a phone call. And it chooses uniformly at random who to call. So with probability 1 over n, it chooses to call this vertex. So the times at which, let's call this vertex V, this vertex U. The times at which V calls U are obtained by a Bernoulli splitting of the rate 1 Poisson process at V. A 1 over n fraction of the splits go to U. So this is the times of these contacts is a Poisson process of rate 1 over n. And similarly, V contacts W here. Also at the rates, also at the jump times of an independent Poisson process of rate 1 over n. Right, this Poisson process and this one are independent because of the Bernoulli splitting. So this is just a property of Poisson processes we saw earlier. If you do a Bernoulli splitting of a Poisson process into multiple streams, the streams are all mutually independent. And finally, V can also talk to itself. And that is another Poisson process of rate 1 over n, independent of the other, and so on. So similarly, between every ordered pair of vertices, there's rate 1 over n of contact. So similarly, W also initiates conversations with V at an independent rate 1 over n Poisson process. Okay, so all these conversations are going on according to independent Poisson processes. So which of these conversations increases the number of one opinions? That only happens, so if a one contacts another one, nothing changes. It already had the opinion, so it's not going to change its mind. Obviously, talking to yourself doesn't change your mind. But it's only if an opinion 0 vertex contacts an opinion 1 vertex does it change its mind and adopts opinion 1. Okay, so what's the total rate at which this happens? For any such pair of vertices, there's rate 1 over n. So this is the rate at which this particular vertex has its mind changed by this particular 1 and changes from 0 to 1. but it can have its mind changed by any of these. So there's a rate 1 over n to every vertex here. Similarly, any one of these could have their minds changed to opinion 1. So we have to count the total number of edges from opinion 0 vertices to opinion 1 vertices. Okay. So there are k vertices here, n minus k there. So there are k times, I had k opinion 1s and n minus k opinion 0s. So let me write it this way, just to be consistent with what I had in the notes just now. Okay, so that was n minus k and that was k. So whenever an opinion 0 vertex calls an opinion 1 vertex, and there are n minus k times k edges between them, and on each of those edges, there's a rate 1 over n Poisson process. So if you look at the aggregate contacts the aggregate contacts from opinion 0 to opinion 1 vertices, that total process is the superposition of all these independent Poisson processes, each of which has rate 1 over n, and there are k times n minus k of them. So the total rate is k times n minus k over n. Okay, so that's one way to see that the rate at which yt, the Markov state counting the number of 1 opinions, that goes from k to k plus 1. It goes from k to k plus 1 whenever one of these nodes contacts one of these nodes. So there's something you need to learn to do, which is, given a verbal description of a process, write down its description, a Markovian description, either in discrete time or continuous time as appropriate. So you have to be able to write down the one-step transition probability matrix or the rate matrix. Most of you are pretty good at writing down transition probability matrices. That's relatively easier from verbal description. Writing down rate matrices might be a bit harder. Let's think a bit more about this. You are still reasoning intuitively in terms of probabilities. So given a Markov process, what's the transition probability matrix over a time period t in terms of the rate matrix? We saw by solving the Chapman-Kolmogorov equations that the transition probability matrices are given as follows. So pt is e to the qt, the probability of going from x to y over an interval of size t is given by the xyth element of this matrix, which is the xyth element of this matrix, e to the qt. Okay, but how do you write down q from a description of the problem? The way to do that is to think about what happens in a very small time interval delta. So p delta is, by Taylor expansion of e to the q delta, its identity plus q delta. Okay, so what does that say? That says that if you pick two states, I not equal to j, then if I is not equal to j, then pij delta, if I and j are different, the identity is 0 for them. And so you only have the second term, so it's qij times delta, okay, roughly. Okay, I guess I should, okay, plus little of delta. Okay, so if you can answer the question of what's the probability that in some very small time interval delta, you go from state I to state j, then you can write down this rate Qij by just dividing that probability by delta. So in our case, what's the probability that yt goes from k to k plus 1 in some small time interval delta? It's the probability that one of these Poisson clocks for going from a vertex in this set to a vertex in that set rings. So there are k times n minus k such Poisson clocks, each of rate 1 over n. By aggregating them, by taking the superposition, you get one Poisson clock of rate k times n minus k over n. And so you're asking what's the probability that that Poisson process has an increment in a small time delta. And when studying Poisson processes, we saw what that was already. So if you have a Poisson process of intensity lambda, then in a very small time interval delta, it has an increment with probability lambda delta. So Qij is just lambda, which for this is k times n minus k over n. Okay. So that's a somewhat long discussion. Maybe most of you saw the answer much sooner than that, but I just want to make it absolutely clear how you write down these rates from a verbal description of the problem, because that's important. Okay, so let's go back to the slides. Okay, so that's the transition rate from k to k plus 1, and the rate from k to k minus 1. So we had two sets of vertices. To go from k to k plus 1, a vertex with opinion 0 had to call a vertex with opinion 1. To go from k to k minus 1, the number of 1 opinions has to decrease. And so that happens by a vertex with opinion 1 calling a vertex with opinion 0 and adopting the opinion 0. So a 1 has to call a 0. Now this graph was bidirectional, so for every edge from a 0 to a 1, there's an edge from a 1 to a 0. So there are exactly the same number of edges going from 1 vertices to 0 vertices. And since there are the same number of edges and the rate is 1 over n on every edge, the intensity of the Poisson process is 1 over n. So the aggregate rate at which 1 vertices call 0 vertices, or the other way around now, is k times n minus k over n. Okay. Okay, so the rate for this transition is k times n minus k over n. Okay, and then we have to be a bit careful about the boundaries. So you cannot go from n to n plus 1 because the state space stops at n. Similarly, you can't go from 0 to minus 1. So we are excluding those boundaries and writing the rates. Okay, but then you ask, okay, so from n you can't go to n plus 1. Where else can you go to? And similarly at 0, you can look at the rates that they go to n minus 1 or to 1. And you will notice that these are absorbing states. Okay, so the states 0 and n, sorry, this shouldn't be 1, and n are absorbing. Because once you are in state 0, that means the number of people with opinion 1 is 0. Everybody has opinion 0. And since the only way you can change your mind is by talking to someone who has a different opinion, and there are no other opinions, you cannot change your mind. You are now, you've made up your mind once and for all in this closed population. Okay. Similarly, if you hit the state 10, then everybody has opinion 1 and nobody changes their mind after that. So these states are absorbing, and it's not hard to see that they are accessible from all other states. Even starting from state 2, okay, you are much more likely to go to 0 than n, but it's possible for you to go to state n. It might be that before, there is some non-zero probability that before anybody with opinion 1 changes their mind, everybody with opinion 0 has changed their mind into a 1. Okay, so because these states are absorbing and they are accessible from all other states and it's a finite state chain, the only thing that can happen is that eventually you either hit this state or you hit that state. Okay, you can't forever remain in this finite set of states because there's some strictly positive probability from any state of reaching these endpoints, and this keeps at any over some fixed time interval. Okay. Okay, so you are guaranteed to hit one of these states, and each of those corresponds to consensus. So consensus is guaranteed in this model. And hence in the original process. So the voter model always reaches consensus on finite connected graphs, and in particular, okay, we've only said this so far for the complete graph. The voter model on the complete graph reaches consensus either on the opinion 0 or on the opinion 1. So, okay, in terms of long-run behavior of this Markov chain, there are only 2 possibilities. And so the question is, the only interesting question is, what's the probability of getting absorbed in each of these states? So what's the probability, let's say, given that we start in state K, that we reach n before we reach 0. And if we do that, then we are stuck in state n forever. Okay, and the other question is, how long does it take? That's a harder question to answer. We'll come to that later, but first we are going to answer the easier question of calculating this probability. So there are 2 ways to approach this. So if we denote this probability by h sub k, it depends on the initial condition k. Then we can, so from state k, the only possibilities are that you go to k minus 1 or k plus 1, and we worked out the rates for doing that. So you can also work out the probabilities for doing that for the jump chain. So you can then express this probability hk in terms of hk plus 1 and hk minus 1. And if you do that, you get a system of simultaneous equations. You get a linear recursion for each hk in terms of its neighbors. And then you can solve this system of simultaneous equations. There are just n of them. You can solve them numerically, but you can also solve them analytically. It turns out that the equations for hk are the same as the equations for the voltages in a network of resistors in series. And there are analogs of this for a lot of other Markov chains, and there is so there's an interesting connection between Markov chains and electrical networks. And if you're interested in the topic, you can look at this book of Doyle and Snell on it. Okay, but we are not going to do that. We are not going to, interesting as that approach is, that's not what we are going to do. We are going to do something else, which is to use martingales. And the reason we take this different approach is that this generalizes easily to arbitrary graphs, whereas solving the recursion doesn't. It only works for the complete graph. Okay, so the next thing we need to do is introduce martingales. Those of you who have done probability 2 will already have seen them. I'm aware that many of you haven't, and I will define these and tell you a bit about them. we will only use one property of martingales in this unit, which is the optional stopping theorem. And so you don't need to know a whole lot about martingales, but it does help to maybe read around a bit more and do some problems, do some worked examples to build up your intuition for martingales, at least in discrete time. So we'll use continuous time martingales, but if you are revising this topic a bit, it's enough to do so for discrete time martingales. And you don't need a whole lot about them, but just a little bit of practice on martingales will be helpful. Okay, I'm going to stop recording, stop this lecture now, and next time we'll discuss martingales.